the screen. Okay. Okay, just continuing our discussion related to ceramic materials. This is another, let me say, field in which ceramic materials, not as bulk materials, but as composite materials, can be interesting, and is the use of this kind of solution in components for gas turbines. As we will see, this is an area in which there are not yet fully consolidated applications, but is a developing area due to also the fact that it is a new area in terms of time. But we can understand the reasons because of these composite materials, especially silicon carbide composite materials, as I need a pen, one moment. No, oof. Just one moment. Come si fa qui? No? Perché non me lo fa più? Just right. Okay, perhaps in this way. Okay. Okay. You see here, silicon carbide, CMC, ceramic matrix composite materials. The first line, that is this line here, is the line in which they are represented the materials temperature related to the metallic part of the blade, starting from, let me say, well-known nickel-based superalloys, and going to the most performing materials that they are still nickel-based superalloys, but are materials for single crystals blades. And you see here that the maximum temperature, the maximum working temperature is something, as we have said many times, around 1050 Celsius. Sometimes, that depends on the design philosophy, it's 1090 Celsius. And this temperature must couple with the temperature of the gas coming out from the combustion chamber, this one. And the red line reported here, this one, and this green line here, is the final temperature which can be tolerated when we are going to use additional solutions, like, for example, thermal barrier coatings we have discussed last time. And so you see there is a relevant increase in temperature of gas is this one, okay, the increase. This one instead is the increase on the surface materials, the outer layer of the thermal barrier coatings, which allow to us to say that actually in the conventional, let me say, application, the gas temperature are something around 1300 Celsius up to, for conventional application, 1400 Celsius. But if we move with a basic materials like silicon carbide composites, and we need to put also in this case on the top, for the reasons that we will see in a moment, our thermal barrier coatings, you can see here that we can reach final temperature of the gas, thus increasing the performance of the engine and all the other questions we have already discussed, up to something which is around 1600 Celsius. So with a relevant improvement in terms of fuel efficiency or increased payload, for example, of the aircraft. This is the reason, because there is interest in this kind of solutions based on composites, in order to overcome the problem that we have discussed last time, which is referred to the conventional bulk, not composite, but bulk ceramics, and related to the low fracture toughness values. As you can see here, the first relevant, let me say, patent about this line, which is something modifying the composition, so it requires of the blades, so it requires to modify also the substrate coating system, as well as the use of innovative thermal barrier coatings, is quite recent. You see here, so less than 10 years. And so the developing time for widespread application is of the order of something which is at least a double of this figure somewhere. That depends on, for example, for land-based gas turbines, it is more than 20 years. Thus, this is a very interesting topic to be monitored, since many relevant industrial companies are working on that, even though, as I said to you before, we do not have still widespread application of this kind of potential and possible solution. This is one example which has been made in the F136 engine from General Electric Rolls-Royce, which is the second choice for this aircraft. You see, that's not a civil aircraft. And also, we do have examples of silicon carbide composite materials used for the fabrication of stator in the third low pressure stage of the engine itself. So interesting thing to be monitored in the next years. We need still, also if we go to the solution of silicon carbide ceramic blade, to, let me say, condition the surface of the blade. As you can see here on this slide, the black part, this one is the silicon carbide, and this white one and this white one are the silicon carbide blade, which are also, in this case, they are coated. Why they are coated? Because this system, silicon carbide, especially in the presence of water steam, which is present in the combustion chamber, can undergo to oxidation phenomena, which can damage in a relevant way, depending also on the partial pressure of oxygen, which is present in the flue gas, which can deteriorate the materials. Just to give to you an example that we also mentioned, but we can write something now. If we have a silicon carbide which is going to react, for example, in a wet environment with oxygen, what it can happen is the formation, for example, of silicon oxide, and then, let me say, carbon oxide or monoxide, that depends, COX. This silicon oxide in this form, with 2 atoms of oxygen, it's a solid material, but if the partial pressure of oxygen is not so much, is not sufficient, instead, it can be formed silicon monoxide, which is a gas. And so in both cases, anyway, in the case we form a solid silicon oxide or a gaseous silicon monoxide, we are modifying, deteriorating the surface of the blade, that is the material properties, and that is the resistance of the material to the stresses to which it must withstand during working conditions. So also in the case of the use of non-oxide materials, composite materials for fabrication of blades, we need to protect the surface of the blades with coatings which have more than thermal and environmental properties, and they act more than thermal barrier coatings instead of, let me say, thermal barrier coatings, since the base materials, it has higher temperature resistance capabilities. They act not exclusively, but mainly as environmental barrier coatings in order to prevent degradation of the materials itself. This is another topic on the field on which many industries are working on, that is the modification of the TBC system. The usual TBC system that we have discussed last time, which is the most diffused, is the partially stabilized zirconia as a top coat. Then we have an M-Crali as a bond coat. Then we have, for example, the nickel-based superalloys. So this means that we have the layer of partially stabilized zirconia and the layer with different thicknesses of the M-Crali. Now we are working on the development of multi-layered coatings. This is one example. You see how many layers are going to be used to fabricate this TBC. This is all TBC, which has a thickness of around 600 microns. So it's comparable with the thickness of the standard solutions, in which adding, for example, different alloying in the metal part, still using PSZ here, okay, but modifying what it was, let me say, the bond coat by using different layers with different metal compositions. We can expect to increase in this case, the thermal insulation properties and the durability of the thermal barrier itself. Also, this is another topic on which, I mean, applied, not basic, applied research and development are going on in these years. Another applications which must be mentioned of the ceramic materials, so we are just discussing, as you see, very few applications in terms of structural parts, but this is the state of the art today, is the use of a special class of ceramic materials, the so-called UHTC, which stands for ultra high temperature ceramics, in order to fabricate protection for reusable thermal protection sheets, TPS, thermal protection sheets. This is the area in which we can find the re-entry vehicles coming from outside the atmosphere and then coming on the Earth and in a cyclic way. And when we are going to move in this area to the standard, let me say, blunt configuration, which is those that you should remember, you can remember, was the configuration of the shuttle, so blunt, to a sharp configuration, like this represented in this picture, which has many advantages for the maneuverability, for example, of the vehicle itself, then we do have a relevant increase of temperatures here on the nose and also on the leading edge of the vehicles re-entering the atmosphere. And so the standard solution, which we mentioned, based on silicon carbide again, and sometimes mixed with silica, which is the standard solution for the fabrication of tiles for the space shuttle, in this case is not suitable, cannot resist to the thermal stresses and to the highest temperature, which are going to, let me say, as you see on the scale, which are going to reach values near 2000 Celsius. And so we need to think to use different materials, and ceramic materials are candidates, and especially non-ceramic, non-oxide ceramic materials are candidates due to their properties in the specific zirconium diboride coatings you see here, which have been doped, which are doped with, again, silicon carbide particles in order to take benefits from the behavior of silicon carbide itself, but protecting in any case the substrate by relying on the behavior of zirconium diboride. These are two examples of objects which have been fabricated, objects on which we also, as a university lab, had the opportunity to work together with the Italian Space Agency. This is a very small picture, this one, in which it is represented a testing made at DLR with a plasma torch in order to test the effectiveness of the solution which have been fabricated and proposed. And in this case, we have another very, let me say, targeted niche application of, we would say again, of composites, ceramic materials, because you see here we have two phases, the zirconium diboride and the silicon carbide, again in the form of coatings. This is an example on how this coating works. You see, this is the outer surface which has reacted with the plasma wind during testing, and so there is a degradation of the coating itself, but this is reusable, so it can be removed and then made again due to the reaction of silicon carbide with oxygen, and that again depends on the partial pressure of oxygen with the formation of silicon oxide. Then there is also the possibility to have reaction of the zirconium diboride to form zirconium oxide. And so we have, during exercise, let me say, a modified distribution of elements till reaching the non-affected part, or also the substrate, which can be also a ceramic based on zirconium diboride, silicon carbide, but usually it is a metallic alloys. This solution can show a very, very high oxidation resistance. That means the protection, what is beneath here, up to about 2000 Celsius with a passive oxidation of silicon carbide, together with a very relevant thermal shock resistance due to the fact that zirconium diboride, which can be fabricated also by plasma spraying with a tailored porosity, has a very significant for the ceramic class of materials thermal conductivity, and this can reduce stresses which are related to thermal shock. Also assuring good mechanical properties due to the strengthening mechanism, which can be put on place by using a formulation which recall the concept of ceramic matrix composites, and then also ablation of that, which is related with high temperature. Other field, just to mention to you, is that of the ceramic armor. In this case, we can find these three classes of materials. These three materials are belonging, in this case, to bulk ceramic, alumina, boron carbide, silicon carbide, most of the time together with titanium boride. So they are very hard material, extremely hard material, and they can let me say, assure their function as armor, obviously for application that you see in the picture, which are not referred to the civil sector. We can move also, as another important field to not forget, to the area of the thin films, those films which are obtained, for example, with techniques which are essentially, in this case, based on physical vapor deposition methods. That is films in which the thickness of the film, of the coating, is something which usually does not exceed 5 microns. So this is the reason because we call it thin films. And is that of the cutting tool. This is a quite established solution. You can find cutting tools like drills, for example, points, in normal shops, this yellow one, which is the most common, says to us that the material is not gold, but the hard steel, which is the gray part, as you see here, has been coated with a thin film of titanium nitride. So again, a non-oxide ceramic materials of the thickness we have specified here, which can give to the component, let's call it in this way, we have fabricated these drills a very high hardness in the surface, thus giving more durability to the object itself during the operation when it is going to be used as a cutting or a drilling tool due to the tribological loads which are applied when used in this way. I have put for you also, let me say, a couple of tables which are reported here, in which you can have at a glance actually which are with the specification the most diffused, I would say in this way, application of ceramic material. And you see they are not so much for what is going to be interesting for us, apart the examples I have made to you before. And you can also see here, just to have an idea, that they can be used, this is another important, because they can also give functional properties, not only structural properties, for which we have to recall the concept of ceramic composites, but they can give to the designer the possibility to rely on a special function, which can be electrical, which can be magnetic, which can be optical, and so on. Also in this way, many times, not all the times, the functionalization of the surface can be made by coatings, but we have also examples of components made by bulk ceramic when we expect a special function of the component itself. Ceramic based composites are used also in these objects. You see here brake disc, for example. They are quite expensive. They are very performing. You can find it, for example, in the Formula One brake system, and they must be composites again. They cannot be bulk because again the pure mechanical properties of a bulk ceramics. So one example which is quite well known is the use of carbon composites to fabricate this object. To those I was referring when I spoke about Formula One brake disc. And why this? Obviously because when we are going to brake, this means that we want to reduce the speed of the vehicles. This means we have to dissipate energy, and energy is dissipated here on the disc in heat. So if we have a material which has a higher possibility to resist to higher temperature, this means that the efficiency of the braking system will be higher. And so the interest for the high temperature properties in terms of behavior, high temperature tolerance of ceramic materials with respect, for example, to metallic alloys. But there is also another interesting to be remembered, which is related. This is not much so clear, but I will explain to you with my pen, to this graph here. In this graph here, we have qualitatively on the y-axis the friction coefficient F, and in the x-axis we do have the time of braking, okay, the time for which the disc is working. And the the dot line, that is this one, is that referred to conventional brake disc, which we can find it also on our automobiles. the continuous line, that is this one, is those which is referred to carbon-carbon brake disc. And what we can see, since the friction coefficient is a very important parameter because it's going to condition the efficiency of the braking system, we do have, in the case of conventional brake disc, a behavior for which, if we put our feet on the brake in our automobile for a long time, then the value of the friction coefficient is going to decrease in a substantial way. And so we have to release our feet from the brake and then let the brake to, let me say, cool a little bit in order to re-establish a suitable way of the friction coefficient. And if we are going to use carbon-carbon, we have a very different behavior, because you see here, we have a very large area in which the friction coefficient is stable. And so you can use your brake for a longer time without any degradation of the braking performance. What is going to be changed? Is going to be changed the fourth part of this curve, which is this you see here. I mean, we do need to put our system to a suitable temperature in order to have this behavior of something which recalls to us a constant value of the friction coefficient. And if you have in mind the Formula One Grand Prix, you have the first part of the race in which you have seen the images, you know, on the television, in which the pilots are going to brake many times, to use the braking system many times. Is the first road which is made, and this is made just to allow to the braking system to reach the temperature suitable for a good performance, so that when the Grand Prix is going to start, the discs are at a good temperature, and then can guarantee the efficiency of the system, of the braking system itself. Now, coming back to structural application, which are the leading, let me say, line of our discussion, here you have some examples of mechanical properties of the most common ceramic materials. These are bulk ceramic materials. Why I want to show to you this? Because here we can see what we have said last time, that is, we are talking about materials which are light, with a mass density which is around 3 grams per cubic centimeter. Now, apart from these two specifications of different fabrication technology for silicon nitride ceramics, we will discuss about this on the next lecture. You can see that we have a very poor, as we said, fracture toughness, something which is some units of megapascal per square meter, apart from the possibility of zirconia when it is partially stabilized, in which we can reach also values approaching 14, 13, 15 megapascal per square meter, with the system we have seen last time by using yttrium oxide as second phase. We see a very relevant resistance in compression, but a very poor resistance when we have a tensile load. This is one thing that we must remember, and this is related to the low value of the fracture toughness of the materials itself. We can also measure the resistance of the ceramic material by using not tensile tests, but bending tests. And this is what is given by the modulus of rupture of the materials, the flexural strength. which gives to us the resistance, the tensile resistance, the tensile strength of the materials, but measured by a bending test. And another thing that we see here is that this value, which is again a tensile strength, but measured in bending, is usually higher than those which is measured by a pure tensile stress. So why all this, and why, let me say, we must remember this? We must remember this, first of all, for one item. Let me repeat to you again. This class of materials, and now I'm talking about bulk ceramic materials, they do have a very good behavior in compression, but a very poor behavior when subjected to tensile stresses. Second thing is the reason because of this is going to happen. The reason is related to the pure value of the K1C. But the reasons is also related to the fact that the defects distributions inside the ceramic materials, depending also on the production processes, but in any case, that's a general statement, always valid, the defect distribution cannot be considered repetitive. And this means that if we have one sample of ceramic materials that we can name, for example, X, a second sample of the same ceramic materials X, made with the same chemical composition, made with the same fabrication process, and so on, we could, for example, during tensile test, have for the first sample a resistance I invent, just to make to you an example, which is 200. And for the second, same, I repeat, same material, same fabrication technology, same test on the lab scales, a tensile strength which is 450, and so on. So we do have a very, very high scattering of the data due to the fact that the defect cannot be reproduced exactly in the specimens, and due to the fact that the fracture toughness is so low, that is, the material is not tolerant to defects when subjected to tensile stresses. And so this requires to us, let me say, a consideration, because we cannot use the same design approach that we are going to use when we have tensile stresses when we use metallic alloys. Because if we make the same consideration for the metallic alloys, I mean, we take one specimen, second specimen of the same metallic alloys, let's call it Epsilon, just to differentiate. Well, for example, for the fourth specimen and so on, for the fourth specimen, we could obtain, let me say, 451. For the second specimen, we could obtain 450.5. So the scattering is very, very low in the metallic alloys. And so we are authorized to make the average of the 5 specimens which are tested according to the standard. And the average of for example, of the tensile strength of these 5 specimens, they can be used for the design also of larger component. Now, in the case of ceramic, we cannot do it because we cannot make an average. If we have the first value, which is 200, the second value, which is 450, the third value, which is, for example, 70. And we need, and that's the key point, we need, for a right design approach, for the ceramic material, with the ceramic materials in presence of tensile stresses, a probabilistic approach. And now let's see, I would say again, because some basic elements I discussed with you some years ago, but now we must go a little bit more deep, which is the approach which can be used, I would correct myself, which is the approach which must be used when we design with ceramics in presence of tensile stresses due to the fact of the very low tolerance to the presence of the defects inside the material itself. We need a probabilistic approach. And the probabilistic approach, which is related to the fact, obviously, that these materials are not able to have plastic deformation, apart some cases of ionic-based ceramic at high temperature, because of these locations, which are present inside polycrystalline ceramics, but they cannot move due to the ionic or covalent nature of the bond, is what is going to result in the use of one distribution, which is the Bible distribution. That this will be applied or can be applied when we start with a ceramic bulk in which we can make the hypothesis that the longer defects, pre-existing defects, is that which is able to break the materials when we apply load. So there is no interaction between defects. And this is reasonable when we talk about ceramics, the advanced ceramics we are discussing, not the refractory, that is the traditional ceramics, because we said at the beginning, last time, that refractory ceramics, they do have porosity values of around 15 to 20%. Instead, when we talk about the advanced ceramic, we have developed fabrication processes in which porosity, which is a form of defect, is very, very low, and the real mass density of the materials is going to approach 99.8, also 9% of the theoretical density, so with a very, very high compaction of the materials itself. So the hypothesis that the defect distribution which exists is a distribution for which there is no interaction, no merging by pre-existing defects, can be considered a valid assumption in the case of this class, the advanced ceramic materials. Then, when we talk about distribution, so probability distribution, we need to remember that, first of all, we have a probability density distribution, which is called also PDF. And if we have in mind a general variable, which is X, which will be for us, for example, the tensile strength of the materials, the density function, the probability density function, is substantially a mathematical expression, because we have different probabilities function that we could use, for which what is true is this relation here. That is, if we want to define which is the probability that our independent variable X is in the range AB, we need to make an integral of the analytical expression of the probability density function, having as the extreme A here and B. That is, we are going to calculate a part of the area which is under the curve described by the probability density function. This is the meaning. Then this has different specification, this mathematical expression, depending on the on the probability density function that we are going to use. You know very well the normal distribution for which we know, which is the value, the expression of fx. The Weibull distribution will have another expression, but we will see it. Then we can also say that in order to build the distribution PDF, we need a lot of experimental data. And this is the reason, because of we must, let me say, by relying on lab scale experiments, we should transform these histograms, which is a discrete function, in a sort of continuous curve. Thus, we need a lot of specimen to be tested, and this is the reason because of we say that for statistical interpretation of experimental data, we need a significant number of experimental points. But this is not a problem. I mean, we know that we must do this, and thus, please just remember that we cannot make any probabilistical probabilistical elaboration of tensile resistance of ceramic, just making, for example, 3 tests. At least, but they can be higher. We should make for each point at least 30 tests. Okay, and so this means that the characterization phase of this class of materials is more, I would say, expensive of those which can be referred to metallic materials. Together with the probability density, we can also define the cumulative function, cumulative distribution function, which is also called CDF instead of PDF. And substantially, this cumulative distribution function represent again an integral of the PDF function. And it is usually used as it is described here. I mean, if we want to define for our variable x, which is the probability to have a value which is lower than this, x not capital, well, we have to make the integral of this curve. So we have to make an integral from -infinity to the extreme x. And this is the meaning of the CDF function. CDF, or F capital, is always positive because it's always an area which cannot be negative. The total area, which is under the PDF, is probability, so is equal to 1. That means that this condition is going to apply. Okay, so if we make the integral from -infinite to +infinite of the density PDF, the F capital will be equal to 1, as well as it is going to be true this other condition which applies when we go on the opposite direction. So this is the reasons I just discussed this with you. What is the Weibull distribution probability? I think we can, let me see, yeah, we have still some minutes. The Weibull distribution probability is, generally speaking, a 3 parameters distributions. That is a distribution which has a mathematical formulation depending on 3 parameters. Even though, for the reasons that we will see in a moment, that is here, that is here, we will have a 2 parameter, which is the Weibull distribution used for the study of ceramic resistance of ceramic materials. And here, this is the formulation. I don't know what is going to happen with my pen. Okay. Why? Okay. Some electronic problem. This is the formulation of the PDF, this one for Bible. And you see, you have here the first parameter, which is M, the second parameter, which is sigma 0, and the third parameter, which is sigma u. X thus represents the value of the independent variable, which are the names which are given to these three parameters in the general formulation. Sigma 0 is referred as the scale parameter. M is referred as the shape parameter because it affects the shape of the distribution. It is also called the Bible modulus. And sigma u is called or location parameter or threshold parameter. And this sigma u is the value, if you see this expression, and this expression is the value for which we do have, if we do have the value of x equal or less than sigma u, the probability will be, the PDF will be 0. So since we want to use this kind of distribution to discuss, to interpolate the data of mechanical resistance, these mathematical conditions would be translated in our terms by saying that if we apply a stress, tensile stress, which is lower or at least equal to sigma u, the probability of rupture, failure probability of the specimen will be equal to 0. These values of sigma u, they are very, very low in terms of absolute value. And thus we can make the assumption to use this threshold value equal to 0, because this is a conservative assumption. That is, we are saying that to any stress we apply, the materials can break. And this simplifies the mathematical expression of the Bible probability density and then of the cumulative probability. And is the Bible distribution with two parameters, which is here reported, which is used for our applications. So you see in this formula, we do not have more the value of sigma u, because we have put this sigma u value equal to 0 in a conservative approach. Then if we make the integral with the concept that we have defined for the CDF, we have defined before, of this PDF for Bible, we get the final expression, which is quite simple here, but it must be corrected, and it will be corrected in the next slides, in which we can define which is the failure probability, PF here, okay? When we apply a stress equal to sigma, tensile stress, to our specimen, and this failure probability is equal to this expression, where we have the scale parameter here and the Bible modulus here. The scale parameter, sigma 0, is going to refer to the stress value, here is written, below which around 63% of the samples, now I discuss the other term, will be broken. So this can be calculated by the list of the experimental data. The Bible modulus can be available by literature, for example, depending on materials and depending on fabrication process, or it can be calculated by using a log-log approach on these expressions, just to eliminate the exponential here, can be calculated by the experimental data. This expression, which is most often written on the textbook, is an expression which is valid with a reference volume, which is called V0, to which the value of sigma 0 is going to be referred. And usually it is said that this is a unitary volume. But this is not the case of our, let me say, engineering component. And this requires to us to take into account something which is not existing in the, let me come back, which is not existing in the metallic alloys, that is the volume effect. So what does it mean? And then we will see next time the modified formulation of the Bible distributions according to the needs that we have. This means that if we have the case of, I write here, if we have the case of a metallic alloys, M, and we use the specimen at lab with a value of the volume, which is V, defined by the standard, then we are going to calculate the tensile stresses and strength of the materials in terms of yielding strength or in terms of ultimate tensile strength. Well, this value on which we make the average in order to have the value that we find on the manuals, on the books, they can be used, for example, for the design of a component having a volume of 1 cubic centimeter, or without any difference for the design of a component having the volume of 1 cubic meter, just to give to you an example. So they are independent from the volume of the component. This is not the case of the ceramic materials. So when we say that we need to modify the mathematical formulation of the Bible distribution formula, taking into account the volume effect, this means that if we make the same procedure of this for a ceramic materials and we make our test on a lab scale, the values that we have found are not independent by the volume of the final component. And what is going to happen is usually related to the fact that the final components are bigger than the specimens which are tested on a lab scale, and this increase in volume decreases even though we are going to use the same materials, the same fabrication process, etc., decreases the resistance of the engineering component. Decreasing the resistance of the engineering component means that it is going to increase, if you increase the volume, the probability of failure of the component itself for the same external applied load. Again, it is a tensile load. So we cannot skip, and this is a big difference with respect to the metallic alloys in the design phase, the volume effect. Why? The reason is very simple. Because the poor behavior of the ceramic materials in tensile is related to the pre-existing defects. Thus, if we have in front of us bigger volumes, this means that the probability to have inside or on the surface of the materials bigger defect is higher. So we can find bigger defects. And if we find bigger defects, given the fact that the value of the fracture toughness is going not to be modified by the volume, this means that the materials can tolerate lower stresses, or if you want, that's the same thing, if you apply the same stress with respect to a specimen having a lower volume value, the probability of failure is higher. And this must be remembered. This must be remembered because we cannot directly translate resistance properties, which are also in a standard way, but measured on a lab scale, to design without considering the volume effect, an engineering component having a volume which is different from the specimen which has been tested on the lab scale. Please remember this, then we will see how the modification is made. It's quite simple. Just let me conclude today with this. Just to give to you an idea of the reasons because of the Bible modulus is called also, as we have written before here, you see, the shape parameter, because you see here, it's a case of a probability PDF, okay? PDF Bible, 2 parameters with a Bible modulus equal to 2. This is a case of Bible module equal to 8, and these are the corresponding CDF by the integral. You see that the shape of the curve of the PDF is going to be substantially modified. And what we can see here is that as the value of the modulus is going to increase, then the width, that is the scattering of the experimental data in terms of resistance, in our case, when the modulus is going to increase, the width is going to be decreased and the scattering is going to be decreased. Usually we do have ceramic materials with Bible modulus which are around some units, 5, 6, 10, 8. When the Bible modulus is going to approach 100 or something near 100, the Bible distribution is going to degenerate in the Gaussian on the normal distributions. So this means that when we have a very strict, a very low scattering of data, as in the case of the metallic alloys, we can use the Bible distribution or we can use the normal distribution as we want, but they are the same distribution. So we use the standard normal distribution that we know. Then we can say that the Bible modulus is an index of material reliability because it affects the scattering of the experimental data. And the further step that we have to do is to how to consider, let me say, the real component volume, but this will be the starting point of the lessons of next Monday. And for today, we finish our discussion. So if you have questions, please ask me.
Professore, mi sente? No, io volevo chiedervi una cosa che non c'entra con la lezione, ma io la prossima settimana in realtà non sono nel turno delle prenotazioni, ma dato che un altro professore mi dà la possibilità di venire a seguire in presenza, volevo sapere se anche lei...
Io non ho nessun problema che lei venga in presenza, però deve essere registrata sul database. Non succede niente, ma se dovesse succedere qualcosa e la sua presenza non è tracciata, poi ci andiamo di mezzo tutti.
Ok, va bene, va bene. Va bene.
Mi dispiace, io
No,
vorrei venire tutti, però...
No, io ho chiesto appositamente, non si preoccupi, grazie.
Grazie a lei. Any other questions? Okay, if no questions, so have a good weekend. We will meet again next Monday. Bye-bye to all. Arrivederci a tutti.
Arrivederci.
Arrivederci.